Questions about anything from last time? Got anything? Had some questions after class about how it could be that Darboux theorem holds, and how could it be that f prime is not continuous? And it turned, you got to think about that for a while. I had to go back and try to remember the example that shows that there's something really different happening here than in just the plain old intermediate value theorem. Darboux theorem says that we assume that f is differentiable on a closed interval AB, and k is between. Oops, I botched this up. K is between f prime of A and f prime of B. Then Darboux theorem says there's a C between A and B where f prime of C is equal to k. And if you knew that f prime was continuous, that would be a snap. That would be the intermediate value theorem. But we don't know that. And somehow Darboux came up with a demonstration that didn't require that. And it's actually so easy that I decided I'm going to spend a couple minutes and do it. Before I do it, there's kind of a lemma we need. Let's see, if f prime is strictly bigger than 0, that implies f is strictly increasing. We need to know that. And if f prime is greater than or equal to 0, that implies that f is increasing. And of course, similar for the decreasing case. So decreasing, etc. Decreasing cases. Similar, etc. And that's one of the cases where the mean value theorem comes in handy because it just falls right out. So the proof to this is nothing. It's the mean value theorem. Namely, f of x, let's do x2 minus x1. First of all, I'm going to assume that x1 is less than x2. Then I would have f of x2 minus f of x1 over x2 minus x1. We know that's equal to f prime of c for some c between x1 and x2. Well, if f prime is strictly positive, then that's going to show that f of x1 is strictly bigger than f of x2. And if f prime of if we only know that f prime is greater than or equal to 0, well, then we just get the greater than or equal to inequality there. And so that's what it means to be increasing. And so it just pops right out from the mean value theorem. Okay, that's kind of we need that when we do Darboux's theorem here. But now the proof of Darboux is fun. I said it was tricky, but it's not really tricky. Let's let g of x be equal to a times x, that's the k, that's between f prime of a and f prime of b, minus f of x. So here we have f prime of a, oh, let's do, I'm going to do a case here. Let me move this. Okay, so the case I'm going to do here is f prime of A less than K less than f prime of B. Then we let g of x be kx minus fx. And here's the thing to observe. Observe g prime at A is equal to k minus f prime of A. And that's strictly positive. And that means g is increasing near there. Okay? So what this tells me is that g is strictly increasing. Near A. Let's see. G prime. Let's see. I don't know that. Not near A, but at A. And then the G prime of B is strictly negative. So that would be K minus F prime of B is less than 0. And that means G is strictly decreasing. Strictly decreasing. And now the only thing left to note is the fact that a function on a closed interval that's, let's see, note, G differentiable implies G is continuous. And we know a continuous function on a closed interval assumes its maximum. So a continuous function on closed AB assumes its max. Okay, and now you think of the graph. Let's look at the graph of G. I'll do a picture proof rather than a word proof. Let's see, it was strictly increasing at A. So we got an A here and a B here. And at A, let's see, I don't know what the value is at A, but I do know that it's strictly increasing. The slope here was positive. And that means that it's strictly increasing for a little bit. That means the max can't possibly occur at A. So A is not the max. And it's strictly decreasing at B. So the slope there, this tangent, is strictly negative here. It's ridiculous. And so over here, it's decreasing into B. And so we see also that B can't be the max. And so the max has to occur someplace between those two. So I'll make a, there. And so the max, this is going to be where the max is. Let's call it x max. Let's call it C. And we know that at the max, so the max happens at maybe multiple C's. There could be multiple humps there at a C that's between A and B, with A less than C less than B. And we know that if a differentiable function has a local max, the derivative has to be 0 there. So that was one of the things we demonstrated last time. We know that f differentiable at C max implies that f prime of C equal, not G is differentiable at C. G differentiable at C implies that G prime of C equals 0. And now Darboux' aha moment was G prime of C equals K minus f prime of C equals 0. So the f prime of C is equal to K. How cool is that? So that's very simple and based on this very simple facts of that section. Okay, questions about that? And so your question at the end of the hour last time about how can you think of a function that's not an f such that f prime is not continuous and yet has that property. And so the book doesn't do you any favors in thinking about that. The book gives you this example. Let's suppose we have I'm thinking of this g of x as the derivative. So g of x is going to be equal to minus, what is it? Oh, I'll make it different. Minus 1 for x less than 0. You can make it be anything for x equals 0, really. And plus 1 for x bigger than 0. That's a jump discontinuity. And notice that that's minus 1 to the left and plus 1 to the right. Oh, by the way, I didn't finish this proof, really. The case f of a bigger than k, bigger than f of b is similar. You can probably guess that you take the function b, f of x minus kx in that case. Okay, so that's a jump discontinuity. And you ask yourself, could I have a function? What if f prime of x was equal to g of x? Well, it turns out there can be no such function that has that property on the whole interval, including 0. It would violate Darboux because that function is minus 1 to the left and plus 1 to the right. Darboux would say it had all the derivatives would have to fill in. There have to be points where the derivative fills in between minus 1 and plus 1. No such animal. It violates Darboux. Okay, so that kind of discontinuity wouldn't be allowed. In fact, if you think about it, you know the fundamental theorem of calculus, even though we're pretending we don't. So what would be the f of x? F of x would have to have a slope minus 1 to the left. So to the left, you know what a slope minus 1 means? It's a line. So it would have to be equal to minus x plus some constant. Okay. At 0, who knows what it is? And for x bigger than 0, it would be x plus some other c. So the graph would look like, oh, it would have negative slope over here, k, and then it would have positive slope over here, and be a c at 0. And of course, that's not continuous. That's that's not continuous. I could make it continuous. So I can make f continuous, but I can't make it differentiable. So the continuous version would be, oh, pick a spot and make them hook up. And how about a spot 0 would be nice. But I certainly can't make that thing differentiable at the origin. So I can make it continuous, but not differentiable. At x equals 0. So then you think about how the heck can I come up with a function. So here's what I want. Question. Is there a g, is there a differentiable f on AB with f prime not continuous? And I had to search my memory for a while to come up with it. It turns out you can't, we showed you can't have a jump discontinuity, but you could have what's called an oscillatory discontinuity. And the classic example for this problem, it's quite easy, is g of x equals x squared sine 1 over x. This is a very oscillatory thing on, how about minus pi pi? Okay, that's clearly different. Oops, that's, doggone it, sorry. How that happens. This is the f I want. This is not the antiderivative, this is the f. Okay, when x is unequal to 0, f prime of x is, you just do the product rule. That would be 2x sine 1 over x. That's continuous at 0. But the other term would be x squared. The derivative of 1 over x is minus 1 over x squared. And we get derivative of sine is cosine. Okay, that is highly discontinuous. So this term is continuous. It's continuous even at x equals 0. But this one has a very nasty discontinuity. Not. It was like hell. Okay, so that's if x is unequal to 0. The x equal to 0 case, I'd have to calculate the difference quotient. Then the difference quotient would be, let's see. I messed up here. Here's what I should have done. This is going to be equal to that, and it's going to be equal to 0 at x equal to 0. Okay. So it's differentiable when x is not equal to 0, but you can see, aha, that there's no way I can make that thing be continuous. So I just need to show that it's differentiable at 0 too, and the difference quotient would be equal to x squared sine 1 over x minus 0 over x, which is x sine 1 over x. And as x tends to 0, that tends to 0. So it is differentiable at 0, and its derivative is 0. And we see that the things unequal to 0 certainly don't converge to 0 as x goes to 0. So that shows that f prime of 0 equals 0. F prime is not continuous. At x equals 0. That answers your question, right? I was embarrassed that I didn't remember that. Okay, well, I couldn't resist going back and thinking about that a little bit after that. And the book doesn't even mention that. They're kind of baiting you to think about it. But it seems like I couldn't even find an exercise about it in the book, so you'd be left to Google it. Questions about that or anything? Well, L'Hopital's rule is pure fun, and that's why I'm going to try to make it fun. The book writes Hospital, but L'Hopital was this is an old French way of writing the O with a hat in Old French stands for an O with an S after it, basically. So that's why it's written Hospital's rule in some books. But I like the old-fashioned way of doing it. And the funny thing, in the book, there's a biographical note that it wasn't actually L'Hopital who came up with L'Hopital's rule. L'Hopital wrote a calculus book based on the notes. So L'Hopital wrote a calculus book based on lectures of Johann Bernoulli, the same guy I talked about on day 1 about Fourier series. Johann Bernoulli should have gotten credit for inventing Fourier series. He should have also gotten credit for inventing L'Hopital's rule. So he wrote a calculus book based on notes for Johann Bernoulli's calculus class. I guess they named enough things after the Bernoullis that they didn't feel like it was necessary. In fact, there's 3 Bernoullis: Jakob, Johann, and Daniel. And they don't even care who's who really anymore. So many things are called Bernoullis something. Okay, well, there's a baby version I think I'll do first. Because it's so easy to understand. And this is what we do in freshman calculus to motivate L'Hopital's rule. Let's suppose we have f of x and g of x differentiable on, how about an interval AB? And I'm going to look at C in that interval. And let's suppose that G, let's see, I need important thing. I need f of C and f of G to both be 0. To use L'Hopital's rule. Otherwise, you get stuff that's pure garbage. Okay. And the baby version says that that g prime of c is unequal to 0. Well, if g prime is unequal to 0, then g can't vanish. Then there'd be I can shrink down the interval. So here's a fact. G prime of c unequal to 0 implies I can shrink down an interval. There is a delta. Such that g of x is unequal to 0 if x is in minus delta, c minus delta to c plus delta. So in other words, this is the only 0. It's an isolated 0. So x unequal to c. That's an easy thing to check. So you would check that just from the definition of the derivative. Okay, that's easy. And so now what do we do? Here's L'Hopital's rule. F of x over g of x. Well, g of x is not 0 in a neighborhood, so that quotient is going to make sense. If x is unequal to 0, x is unequal to c. So, and, okay, I'm taking here x unequal to c. And x in that little delta. So x would be in that little neighborhood. I guess the book calls that a neighborhood. V delta about c. Okay, so now what do you do if you're in freshman calculus? You say, well, this is f of x minus f of c is 0. So that's 0. And on the bottom, I'd have g of x minus g of c. It's also 0. And I realize, oh, those look like difference quotients, kind of. And so I multiply and divide by x minus c. And now I know rules of limits. This thing on the bottom has a non-zero limit. And since it's in the denominator, that's going to tend to f prime of c over g prime of c. So that's the baby version of L'Hopital's rule with a very simple proof. Freshman calculus kind of thing you can motivate. But in this more advanced book we're reading now, in freshman calculus, after we do that, we say there's lots of other versions that are true, but we're not going to demonstrate them in class. So the fact is, there's lots of fancier versions. So, you know, there's indeterminate forms. Indeterminate forms. Basic baby one was an indeterminate form 0 over 0. But you can also do indeterminate forms infinity over infinity, etc. And then when you're in freshman calculus, you do 0 times infinity, and what else can you do? 0 to the 0. They're all interesting and fun. And you can mess around and demonstrate them using sort of the similar ideas to the ideas in this section. When you start trying to list them all and prove them all, it gets kind of tedious. So I'm going to simplify the whole business here and let you read 6 point whatever this is, 3 carefully. But the improvements are based on a famous thing. Are based on I guess in some books I've seen this called the extended mean value theorem. In the book it's called Cauchy's mean value theorem. Cauchy's mean value theorem. And let me state it carefully. Let's suppose f and g are continuous on a closed interval. Differentiable on the inside. And g prime of x is non-vanishing for x in AB. Then there is a C between A and B. With, let's see, f of B minus f of A over G of B minus G of A equals to f prime of C over G prime of C. So that's an extension of the mean value theorem. A remark is that if I took g of x equal x, that would be the mean value theorem. Would it be? Yeah. That's the extended mean value theorem. And so that allows you to get more and more sophisticated versions of the L'Hopital's rule. I'll let you read the statements in the book. From the point of view, since I did some technical stuff already, I don't want to get bogged down. But if we knew a little bit more, for example, if we knew that f prime was continuous, then so here's a second baby version. If we know that f prime is continuous too, f prime and g prime are continuous, and we have f of c. Oh, let's see. I want to choose. We know f and g are continuous, and we have f of, pick a point, x naught equals 0, and g of x naught equals 0. Okay, then if I want to calculate, let's see, I'd write f of x over g of x. I could write that as f of x minus f of x naught over g of x minus g of x naught, since so I'm just subtracting 0. And then I would use the extended mean value theorem here and write that as f prime of c over g prime of c, where c is between x naught and x. So now if I let x go to x naught, then c is going to be stuck between there. C would go there too. If x tends to x naught, then c that I get, that c is going to depend on x. Then c, that would be something that depends on x, tends to x naught too. And the continuity and the non-vanishing of g prime, so here's what we know, that are continuous. We know that g prime of c is not equal to 0. And so that thing would tend to, that the limit as x tends to c, it's funny, I never stated what L'Hopital's rule is. It's f of x over g of x is equal to the limit as x tends to c of f prime of x over g prime of x. And that's pretty simple proof once you understand the Cauchy mean value theorem. Well, the proof of the Cauchy mean value theorem is easy, yet mysterious. So here's the proof of the Cauchy mean value theorem. Pull this function. This symbol, colon equal, means h of z x is defined to be. And here's what they define it to be. I'm going to define it to be f of x minus f of a minus f of b minus f of a over g of b minus g of a times g of x minus g of a. So proof of Cauchy, I would say it's mysterious. But nothing's really mysterious in math. Cauchy sat around and thought about it a long time, obviously, and had some inspiration somehow to cook up this function. And this function satisfies the conditions of Rolle's theorem. Notice that it's 0. H of a is 0, and h of b is 0. H of a is clearly 0. That's a no-brainer. But it's also 0 at b. So there's a place in between where h prime of c is equal to 0. So you get a c with h prime of c equals 0. And when you calculate h prime of c, you get first f prime of c there. Minus f of a is a constant, so its derivative is 0. This ridiculous thing is a constant, so it just sits there. And then the derivative of that last thing in parentheses is g prime of c. And that's going to be a big fat 0. And so when you put that stuff on the other side and divide by g prime of c, you get the conclusion of the theorem. So sneaky. Well, how the heck did Cauchy think of that thing? Where did H come from? Exclamation point. Well, here's the picture. I'm gonna do an R2 curve. A curve in R2. Parametrically defined by x is f of t and y is g of t. Then that's in the R2, that's going to start at f of a, g of a, and go to f of b, g of b. And let me make a line between those two. The slope of that line is the quotient we're interested in. And so what might this curve look like? It's going to start here. It could wiggle around and do weird stuff like this. See that? How weird can I be? And what I'm looking for is a point that looks like a max here. At this point here, I would get a tangent line like that. And the derivative of that tangent line, let's see, what's this tangent vector? There's that purple dot. This tangent vector would be equal to the vector f prime of c times the I vector plus g prime of c times the j vector, where that max is. And the slope of that line is f prime of c over g prime of c. And so now that I don't know things like Rolle's theorem, I think, how in the heck could I find a C like in that picture? And of course, I'm thinking of Rolle's, and it would be obvious to pick this orange line and maximize it. But it turns out that orange line is harder to write down a formula for. And here's a green line. This distance is not so hard to write down. And h of x is basically that distance. So that's how Cauchy came up with his brilliant idea of pulling this function out of the thin air. Questions about that? And remember, that orange line is proportional to the green line because there's an angle there. And so it's just a trig. Wherever that orange line has a max, the green line has a max. Because they're just multiples of each other by a trig angle, sine of something. So that's where Cauchy had his brilliant idea. And the funny thing, it's not like a function, because the thing can wiggle around and it's not single valued. But still, at that max, you'd expect the Rolle's theorem to kick in and give you the proper slope, and it does. Let's see, what should I, oh. So I'm going to let you read about all the different versions of L'Hopital's. I thought I'd apply a couple of them. Oh, here's a fun one. Let's see. I look at 1 over x minus 1 over sine of x. This turns out to be a very important thing to calculate in the theory of Fourier series, surprisingly enough. And so let's see, as x goes to 0, that's going to look like infinity minus infinity. Let's go to 0 from the plus side. Otherwise, it looks even worse. So x is going to go to 0 from the plus side. It's going to be the indeterminate form plus infinity minus plus infinity. Well, it's a typical thing to do to turn this into a different kind of indeterminate form. If I do cross multiplication, I get sine of x minus x over x sine of x. And that's, now that when I let x be 0, that's 0 over 0. And so if I let this be f of x on top and g of x on the bottom, I have 0 over 0 at x equals 0. Let's see, what would be f prime of x over f prime of x? G prime of x. That would be cosine x minus 1 over sine x plus x cosine x. And the ouch is, that's 0 over 0 again. But if I do it one more time, then I get f prime of it, f double prime over g double prime. Its derivative of cosine would be minus sine of x. Derivative of sine is cosine x. Let's see, I'd get 2 cosine x from the other one plus x times minus sine of x. And as x goes to 0, that would be 0 over 2. That's not indeterminate. That has a limit. So that's not indeterminate. And now we use L'Hopital's rule on the second derivative case. So the limit as x tends to 0 from the plus side of f double prime over x over g double prime of x, well, that's 2. What is it? No, it's 0. 0 equals that. And we use L'Hopital's once here and say, aha, that's the limit as x goes to 0 of the first derivatives. And we didn't know that thing existed a minute ago. But now we do know it existed. It exists. And so here I've used L'Hopital's rule. And now the aha moment is I can do it again. So I didn't know that when I started, but now that I know that this limit exists, so